Welcome to PCB Chat, where we talk with experts across the printed circuit design, manufacturing, and electronic supply chain. I'm Mike Buteau, president of the PCEA. Today's podcast is sponsored by PCB East and the Ultra HDI Forum, Engineering Tomorrow's Electronics. Join engineers and designers this June in the Boston suburbs for more than 75 hours of technical presentations and an exhibition featuring 65 leading companies from across the printed circuit design to assembly supply chain. Visit the website at pcbeast.com for information. Today, we welcome Sergiy Nesterenko. Sergiy is founder and CEO of a new software company called Quilter, whose goal is to accelerate hardware development by fully automating circuit board design. Easy, right? Sergiy came from SpaceX, where he was an EMI and radiation engineer. He founded Quilter in 2021, and the platform launched last year. He's also raised $10 million in Series A funding, so either he's really onto something here or he has some very wealthy friends. So welcome, Sergiy.
Mikey, thanks so much for having me.
As we dive further into the world of artificial intelligence and electronics design, we have to come to grips with the fundamental hang-up many designers have with regard to turning over routing and parts placement of their boards to the CAD tool. Now, some designers point out that the autorouters have been part of their tools for decades, and they are all built on some form of machine learning, but those same autorouters are often ignored in practice because they don't complete the designs to the satisfaction of the users. Now, that's a fact that often gets glossed over or completely ignored by developers of AI-based platforms. Yet you have acknowledged this head-on, noting in the past that the problems inherent in autorouters. So can you explain your thinking here?
So I think from my experience, most people just don't use autorouters, right? Like when you go to, my previous company at SpaceX, you look at any flight board, it's a bunch of people who are choosing the stock ups, who are placing components, who are, routing boards, and who are thinking about the physics of everything. And of course, that's time consuming. For a complicated board, that's easily weeks or maybe even months of work, and that's a problem. So I think that, the motivation to automate this is basically to just go faster and to build better boards, right? So it's a clear need if it were to exist. And the question just becomes, why doesn't it yet exist? Why hasn't it built? And why is everything that has been built not good enough? So where I think autorouters kind of fall apart today is in maybe three major areas. The first is that they typically don't tackle the entire job. So typically, you are still responsible as the user to configure the stack up. You're typically responsible to figure out what fabricator you're going to use and enter in the manufacturing rules. If you have any special considerations like differential pairs or impedance control, you have to encode that into basically geometry rules yourself. You typically have to do the placement yourself still. And then even when the autorouter presents a layout, you still have to review it and make sure that it's actually going to work. The second problem, so that's a lot of configuration and setup and a lot of things that are just simply not even tackled by the autorouter, as opposed to somebody actually doing the full layout. The second problem is that with a board of any complexity, autorouters usually just don't complete the job. Like it's very common to click on the autoroute button to see it get to, say, 90% of a design, even if the design is only a couple hundred components. And then you'd think, oh, I only have 10% of the work left to do. And you quickly find that the autorouter just didn't leave you room to route the last 10% of the traces. You have to go back and delete everything and restart. That's another problem. And then, of course, the third problem I already alluded to, which is that you then have to review the autorouter's work. Like even if it completed everything, you have to look at every single trace and ask yourself, is the signal integrity here is going to be good? Is the crosstalk here going to be too much? Did it consider, my high current traces? Did it consider, so on and so on and so on and so forth? And that is arguably just as difficult as actually just doing the routing yourself and following the rules that you've built up over time. So the place that we're coming from is that in order to achieve full automation, right, in order to really, really solve this problem, we have to solve all of those. We have to tackle the whole problem. So start with the schematic, ideally, and do the whole thing. Identify the manufacturers, respect all of their rules and tolerances, do the placement, do the stack ups, and do the full routing with all of the physics included. You have to complete the job. Right, a board that's routed to 99.9% is a broken board. So anything short of 100% is not acceptable. And you have to account for the physics, right? You have to show the user that you've considered signal integrity and crosstalk and all of that stuff such that the schematic still fundamentally works.
That physics thread, I think, is going to be repeated throughout our conversation, but I'm gonna pause on that for a moment and just let's start a little bit higher up. What does that schematic to layout process look like? Is there any human interaction needed here under the Quilter platform?
Yeah, so the way that we do this, so first of all, one of the opinions that we take is that we shouldn't try to get you, the user, away from the tools you already know and love. So, for example, like if you're used to Altium, it's obviously a popular choice. We are not trying to come in and say, "Hey, stop using Altium, learn this new platform." That would be a big lift for many organizations. So, what we do instead is we ask you to basically take your Altium files as an input, drag and drop into Quilter. We do our work and we return the Altium file back to you. So you can kind of continue and do reviews and generate manufacturing files the same way you would have. From the user's perspective, what we really expect is that you've finished your schematic completely. At this point, we still ask the user to define the footprints. And the reason there is that a lot of companies have their own footprints libraries that are not externally shared. And so they want to have their own control over those. And so at that point, you have a board file where the net list and the footprints have been loaded. And then perhaps you've defined the outline of the board and maybe pre-placed some connectors where you know they have to go in a specific spot. Everything else stays off the board, and that's what you're inputting into Quilter. A good model for this is if you were to hire an external layout resource, like a contractor to do your layout, think about what you would email them. And just instead of emailing that person, you're drag and dropping that into Quilter's website.
So that's one of the more novel aspects to this, from what I understand. So the user is going to pull the files from the native environment into Quilter. Will it still look like, for example, the Altium environment inside of Quilter, or will it look like, does Quilter have its own user interface?
So Quilter has its own user interface. And on purpose, Quilter's user interface is not meant to be complicated, right? The main thing that Quilter has to accomplish in a conversation with the user is to understand all of the schematic, and in particular, all of the signal types that are happening throughout the schematic. So this is, one of our areas of growth is to understand where do you have high currents, where do you have high speed, where do you have differential pairs, where do you have impedance control, because that information isn't necessarily kind of encoded in the schematic. But after that point, Quilter's aim is to do the layout for you, right? The inspiration we use internally is that doing the layout for your circuit board should feel like compiling your code. Right. If you think about it, like a schematic is a little bit like a programming language. And then a circuit board is really just trying to actually make that schematic happen in real life without screwing it up. That should feel more like compiling your schematic than actually doing the layout yourself. And so the interface for Quilter is simple. And so for that reason, it doesn't necessarily look like Altium or KiCad or any of the other tools.
Okay, so those are two. You mentioned KiCad there. That's another one of the CAD formats that you work with, correct?
Correct.
Yeah. Any others of note?
Yeah, so Altium and KiCad are the main ones we support today. We actually had initially built out support for Eagle, but that seems to be shutting down for the most part. And so we're not supporting that anymore. The next ones we're looking at adding are most likely Cadence. Cadence Allegro is most likely to be the next one we add.
And do you have to develop, kind of VAR agreements or any type of technology transfer or shared agreements with any of the CAD vendors in order to develop this?
Yeah, that's a fun question. So thankfully, like legally speaking, reading and writing common file formats is not something like we have to go get agreements for. But like we like to work with the companies because it's easier for us, and in general they've been supportive. So with Altium, they've been very supportive of us doing this so far, and have extended some support from their engineers in helping us work with those files. We haven't worked with somebody at Cadence yet, but if somebody's willing to, I'd be happy to.
Okay, well, if anybody from Cadence is listening, here you go. So, Sergiy, let's talk about the types of boards that you have used as proof of concepts and that you've successfully routed to date. Let's just start at the hardest part, right? What's the most complex board that you know of that's been designed using Quilter? Meaning like how many layers, how many pins, DDR3 or 4 memory, anything like that on it?
Totally. Yeah, so I think of complexity roughly in two dimensions. One is just kind of the raw combinatorics and geometry. So that's roughly how many pins, how dense is the board, so on and so forth. And then the other is physics, right? What are the most interesting signal types that you've captured? So starting on the physics side, the most interesting board we've done to date is actually one of the, or at least the ones that we've personally brought up within Quilter, is one of the open source projects from OpenMV. So they have a really cool set of computer vision boards where they basically have an onboard camera. I think it was an STM32 that we did, an SD card, USB, things of that nature. Running onboard live computer vision for basic like face detection or basic neural network on board or whatever else. So that's an example of something that we had done on the slightly faster side. I think that was a 500 megahertz processor. We're pushing in the next probably 6 to 8 weeks to release support for much faster differential pairs and impedance control. So that'll allow us to get into the kind of multi-gigahertz territory for signal integrity, which will be really fun. I'm really excited for that. On the combinatoric side, the kind of biggest boards that we've done are unfortunately not public. They've been for companies, and I can't reveal them. But you can imagine kind of big test boards. So if you imagine a board that's maybe, I don't know, 15 by 30 inches, something of that nature, with maybe 400 or 500 components, close to 2,000 pins, and nothing super high speed, nothing more than a couple of amps, but still just a lot of parts, a lot of things to connect. And I believe both of these were 4-layer boards. I think we've never gone so far above 6 layers.
And how long did it take for that for the tool to route that board?
We've obviously improved drastically since we've done both of those, but both of those should be running in about 2 to 3 hours by now.
2 to 3 hours. Okay.
Yeah.
So start to finish, 2 to 3 hours. Wow. By contrast, then, when you were working in your previous life, just setting up the constraints probably took 2 to 3 days, right?
Yeah, definitely. The company that we did the big board for, the engineer that we worked with estimated that whole board would have taken them about a week to do.
Mm-hmm.
That's very much our focus, right? Like the major pain that I felt while at SpaceX with designing these boards is that, layout is a bottleneck. Like you can't put 5 people on it and get it done in a day. And so you're waiting for your first prototype for 5 days or for 10 days. And you're going to have to do multiple of those iterations before you eventually actually go into production. And since it comes at the end, it becomes critical path. And so the ability to shorten that is very valuable for a fast moving company. And the other thing that Quilter does that's interesting is, because it's done in software, we don't just lay out one board, we lay out hundreds. And so we can have a 2-layer, 4-layer, 6-layer variant across multiple different manufacturers, multiple stack ups, multiple design rules, and multiple trade-offs, all in that 2 to 3 hour time. And so I think that is what empowers engineers to prototype much more quickly using Quilter.
Let's talk a bit about the intelligence part of the AI. How does Quilter learn?
Yeah. So the way that we approach this problem is by using a kind of a small subfield of AI called reinforcement learning. So most people will have heard of this technique from learning about how DeepMind defeated the world champion at Go about 5 years ago now. So the idea there was that they created, an implementation of the game Go within a computer, and then they taught the AI to sit on both sides of the board and basically play against itself. And then whenever the neural network won a game, it would be changed in such a way as to make those moves more probable. And whenever it lost a game, it would change in such a way that it would make those moves less probable. And after hundreds of millions of games, the neural networks found strategies for playing the game of Go much better than a human, and famously, of course, defeated the world champion. That's very much how we approach this problem. So, a lot of people think that we would have taken a whole bunch of human designed boards and learned on them or something like that. I actually think that's a mistake for a number of reasons, even if you were able to get that to work well. So what we think of it as is that the neural network and other algorithms, it's not all just neural networks, are playing this game of layout, right? Where do I put the components? What stack up do I choose? How do I connect everything? And then once we have that kind of candidate locked in, we can then run a bunch of physics and heuristic evaluations to figure out, basically, is this board going to work? Yes or no? And if it's going to work, then the agent becomes more probable to make a design like that. And if it doesn't, then it won't. And so it's really playing the game of layout, being graded by physics.
So I want to yank on that thread a little bit, where you noted that you think it's a mistake, and I'm paraphrasing here, so correct me if I'm wrong, but it's
Sure.
a mistake to try to take the human decision making process and apply it. Am I stating that appropriately?
Yes.
So what is it about that you feel is misguided?
Yeah. So it's there's two main problems with it, right? And it's not to say that humans haven't developed great strategies. They surely have, and many of those are useful as kind of shortcuts in this process, right? So many things that we'll do will look kind of human because we take inspiration. But from a first principles perspective, the biggest reason that I think it's not a good idea to build a company on learning on existing board designs is that humans aren't necessarily the greatest at designing circuit boards, right? Many boards fail to function on their first bring up. Many boards fail EMI on their first test. So already you have an issue that you are learning from a corpus of data where mistakes are probable. The second issue is that humans have to reserve a lot of margin, right? If you're looking at a board that's going to take you a month to do in layout, your worst case scenario is coming up against that deadline, finding out that you couldn't quite fit everything, right? The components don't fit, or the routes don't fit, or you have to make it bigger or change the stack up. And all of a sudden, you have to undo and add 2, 3 more weeks of work. So, to avoid that, humans will start with a board that's a little bit too big for what's strictly necessary, a little bit too many layers for what's strictly necessary, with more margin on clearance and trace widths and separations than strictly necessary, just to make sure that it works and is on time the first time around. So if you learn from that data set, that's the best you'll ever do. Whereas if you learn from first principles physics, you can eventually make boards that are better than humans can. You can eventually eliminate layers. You can make it smaller. You can make it more performing. You can violate some of the rules that humans kind of have off the cuff, but that the physics says is actually going to work and actually going to pass. So the potential to make boards that are better than what humans can do is the main reason for me. The second reason is just simply that there's not a lot of good open source designs out there, right? Like the best boards are locked behind, key at Apple or at, SpaceX or whatever, and they won't want anybody training on those boards. And even if you could collect them all, there's maybe thousands or tens of thousands of them, which is typically not enough to train machine learning systems. And so those are the two main reasons that we go after reinforcement learning rather than supervised learning.
So one of the things that appears that's really differentiating you, I think if I go and I look at many of the AI-based platforms, they use actual designs as teaching tools. And what you're kind of saying is that it's not worth the effort to try to extract from the design what the intent of the designer is, because even if you could do that, that intent might be fundamentally flawed.
Yeah, I think it's a matter of what level of intent you're talking about, right? So it's very critical for us and for anybody else to understand that the designer expects a 4 amp current on a certain net, or a 2 gigahertz impedance controlled signal, or whatever else. That's really important. You have to respect that rule. You have to verify with physics that you did it right. Otherwise, the board just simply won't work. But I think the mistake that most other AI approaches take is that they are looking at the fact that the designer followed, say, the 3 widths rule for isolating crosstalk, right, or something like that, and they're optimizing for making designs that just replicate that, and you're effectively replicating a heuristic that humans have found to then really solve the real problem, which is I want to make sure my crosstalk is good enough isolation between these two pairs.
Obviously it's one thing to say that a net is functional, right? It's connected, but the uh,
Yep.
how do you then I guess it's another thing to say that this is actually a buildable design, right? Because when we talk about something, whether it can work, which is something you noted earlier, that and comes down to the physics of the manufacturing plant, right? And their ability to actually make it in a way that it's functional. How do you determine, if the board itself is manufacturable? I mean, do you try to train on the constraints of the fabricator as well?
Yeah, so the way that we do that is one of the convenient things in reinforcement learning is that you can explicitly force constraints onto your agent that cannot be violated. So, for example, I'll give a really simple example. Very obviously, you can't have two components colliding on your board because then you couldn't solder them and it couldn't work. So, instead of allowing the neural network to place components in such a way that they're colliding and letting it learn that they shouldn't collide. In reinforcement learning, you can simply make it impossible for them to collide. And that's convenient because then you don't have to spend all that time for the network to learn that very, very basic fact. The same thing is possible with the manufacturing tolerances. So the way that we approach this is within Quilter, there are, currently about 18 or 20 different combinations of like stock ups, design rules that are sourced from manufacturers. And different manufacturers, of course, have different tolerances. So then those constraints are hard constraints that the agent must respect. So effectively, Quilter is trying a generic stack up, something that's like, I don't know, 4 layers, 10 mil traces, 10 mil spacing, something that basically any manufacturer can do. And if that works, fantastic. But if your board has very, very small components, very small pins, that's not going to work. And so then Quilter tries everything down to like a 3 mil trace width with 3 mil clearance that only some manufacturers are confident in doing. And then we'll kind of identify that, hey, for this board, you're going to need this manufacturer that can handle that kind of tolerance. So that's, instead of training on those constraints, we just take them as actual constraints.
So then if somebody wanted to do package on package?
That's not something that we've considered to this point, to be honest. Yeah.
Okay. I'm just thinking in terms of the example of two components colliding.
Yeah.
But I mean, your point is well taken, right? I think that the bigger question here that I have is simply that as the manufacturing capabilities change, how do you ensure that the platform itself stays up to date?
Right. Yeah. So for us, that literally looks like a laundry list of like, what are all the manufacturers we're aware of? What are their tolerances? And frankly, right, as manufacturers improve their tolerances and can support smaller features with lower clearances, that's music to my ears. That makes the combinatorial problem much easier. And then we are more successful with more boards. So for us, keeping up with manufacturers is just a matter of adding an entry to a database that says, hey, this new manufacturer exists, or this new capability exists with this new kind of stack up, these new tolerances.
Thank you for all that explanation. I really do see a difference in terms of the way that you're fundamentally approaching this versus some of the other AI-based tools out there, either by startups or even by some of the very large ECAD companies. Let's talk about the company itself for a moment. How many staff do you have, and what are their roles?
Sure. So we, as you mentioned, we've been doing this for a few years now. Until now, we've been mostly in R&D mode. I think most people don't appreciate that this is really an ancient problem. Like the first papers I've ever seen of people doing actually both placement and routing at the same time in an algorithmic way date back to the early 60s. So people have been researching this for 6 decades without really a practical solution in the market. So just to acknowledge, this is very, very difficult, and we fully expect that. And we've built a company in that way. The vast majority of our staff, we're about between full-time and part-time and contractors and everybody all involved, we're approaching 20 people. I think we're about 18 or so right now. The vast majority of that is engineering. So we've obviously got a lot of folks on, the kind of what we think of as the compiler. So all of the algorithms and modeling required to represent boards, to manipulate boards, to input them from Altium, export them to Altium, even classic algorithms that do some amount of exploration in the design space, and of course, machine learning, reinforcement learning folks who do the training of models where that's appropriate. We have a team that's focused on the application itself. So that's the website, the servers, ingesting your files, talking with the user, validating the input files, things of that nature. And we're starting to build up a product and design function as we are, reaching more and more away from just pure R&D and into serving users, serving customers.
And so, in your past role at SpaceX, you were an electronics engineer. Were you responsible for board design in any way?
Not for flight boards, but for test boards, yes.
Test board.
So in particular, most of my time there was spent on radiation effects, basically ionizing radiation. Please don't kill the rocket. And most of that work is around, good parts choices, schematic choices, subschematic subsystems, redundancy, things of that nature. And I built a fair amount of boards myself to support that kind of testing, and had input on the design of the actual flight boards to make sure their reliability is sufficient to survive flight.
Was there a eureka moment when you said, hey, look, I want to go off on my own and create this product because it's a problem that I see us running into here, and I hear from other companies about the same?
So ironically, the eureka moment came 5 years before I left. I sat down to do my first board hadn't learned Altium before, was learning it for the first time. Asked myself, why am I doing this? Like, a computer should do this. Tried an autorouter failed. Said, okay, I guess I have to do this. Built the board, got it reviewed by a few other senior engineers, make sure it was all okay. Uh, got it brought up, and it caught on fire in my hands. So I then kind of just took it as fact that this is how PCB design goes, and I better get better at it. And it wasn't until 4 or 5 years later that I saw that it's possible for me to go and start a company and raise venture capital and all these things. And I married that with the okay, well, what did I really suffer from in my job? What is the big bottleneck that I saw within our departments? And those two came together in the kind of, all right, let's start this moment.
So how do you go from that to neural networks and machine learning? And I mean, did you take classes in coding and so forth?
Yeah. So my undergrad, I actually was all in the sciences. I triple majored in math, physics, and chemistry, just to get a really good base for basic understanding. At SpaceX, a lot of my job was actually programming because I had to do a lot of statistics. So it wasn't enough to just screen parts and see how they do in radiation environments. I had to ultimately be accountable to the customer, and in particular, the biggest ones at the time were the U.S. Air Force and NASA, that their payloads were safe with us. And so I'd have to figure out from all of the different inputs of the entire environment and the entire rocket, what is the final kind of probability of success that we're accountable for. And so that was a lot of statistics and simulations. Around that time, 2015, 2016, early neural network applications were starting to come up. And it kind of became self-evident to me that was going to be important. And so I just took my own time on the side to learn all the math behind neural networks and backpropagation, write it out from scratch. And I kept playing with them for the next 6-7 years before getting to Quilter and kind of being here. So partially self-taught, partially school, partially experience on the job.
So triple major. So you kept your advisor pretty busy there, I guess.
Yeah, I had to go to 3 different advisors to make sure that I could actually complete all 3 majors. That was fun.
You announced a $10 million funding earlier this year. Can you share details about the company valuation?
No, we haven't made the valuation public yet.
Do you feel any kind of pressure to succeed given that kind of funding?
Of course. I mean, it's honestly. I personally feel pressure from all directions, right? I mean, I started the company because I wanted to see this work, and so I feel accountable to myself to make it happen. Of course, the investors who were willing and brave enough to bet on us, and there's many other than the Series A round. We did a few rounds before that, and so I want to do right by them. Most importantly, probably are my family and my employees, right? We've got dozens of people here who are supporting us, and it's not just the people working at the company who have to carry the burden and take a risk. It's all of our families as well that have to support us, and that's very, very meaningful. At the end of the day, working at a startup is much harder in a lot of ways. It takes a lot more hours, takes a lot more time, and typically for less pay, unless it actually works out. And so I really appreciate the risk that everybody's taking with us, and that's what gets me up every morning bright and early to make it happen.
I want to remind listeners that today's podcast is sponsored by PCB East and the Ultra HDI Forum, Engineering Tomorrow's Electronics. Visit pcbeast.com for information. Understanding, of course, there's a lot riding on all of this. I keep going back to this idea. The surveys that we've done, suggest that maybe only between 5 and maybe tops about 20% of boards are auto-routed at all. Okay, most of them are hand-routed, and so tens of thousands, hundreds of thousands of hours maybe each year are spent doing everything manually. Right? Congratulations for the idea. Congratulations for convincing other people of your vision and getting this far. Let's talk a bit about your roadmap. So, you touched on it a little bit a while ago, but if we talk 2 years down the road from now, what goals do you have in place? Where will you be at that point?
Yeah, that's a good question. So I roughly view our core technical compiler roadmap on the same 2 axes identified as the complexity earlier on. So one is just kind of combinatorics and solving boards, and the second is physics. So as we improve the kind of geometry engine and the exploration of different geometries of the boards, that's what eventually allows us to go from three, four, 500 components, 1 to 2,000 pins, to eventually tens of thousands of pins, and eventually, hopefully, the big monster boards in the networking applications that are hundreds of thousands of pins. So that's one thing that we'll obviously be pushing. Simultaneously, it's also very critical for us to push on the physics side. So I'll give an example. Like today, if you log into Quilter right now, you'll only see support for the very basic thermal considerations of currents. Within the next 4, 6, 8 weeks, we're hoping to push a support for impedance control and differential pairs, which gives us ability to do some more high speed, specifically high speed digital is what we're thinking about the most right now. Of course, over time, we have to add support for things like switching converters and power supplies and antennas and analog circuits, and ESD, and so on and so on and so on and so forth. So I hope that within 2 years that we're talking about some very serious boards, right? Some boards that are FPGAs or CPUs with DDR4 that would have taken a human a month or a month and a half to do, that we're able to do fully autonomously with kind of the physics guarantees that the user would need to trust the layouts that hopefully work on the first try. Maybe we'll have some demonstrations sooner of that, and that's certainly my hope, but we'll see.
What does the typical user look like today? And are you able to aggregate any of the data based on how they're using the platform?
Yeah, so to be very clear, like we don't train from human boards. So anybody submitting boards to us, that's not the input that we take, because people are obviously very concerned with the privacy of their boards and the fact that their boards aren't being reused for other vendors. So that's very important to state. The kinds of users that we're seeing now, I mean, we're in an open beta for a reason. We welcome everyone to come try it out. It's not going to be a great application for everyone yet, just because we can't do a lot of things that we want to do. But we see everybody from people actually trying to do serious big board designs that are thousands of pins, to people that are kind of adjacent. So think about like firmware engineers, mechanical engineers, test engineers who need a design to de-risk and work on their prototypes, but maybe aren't building like the flight design or the main production design that's going to go into a big product. And of course, all the way down to hobbyists. Like I saw some keyboards come through in the last few days. I've seen some basic radios and things of that nature. Lots of like Raspberry Pi and Arduino applications, which are fun. But I think today, like where the product is the most sticky is within those, what I think of as like supporting boards, right? So if you think of like a SpaceX flight computer, we can't do it reliably yet. So the person designing that, we can't really help. But if you think about a person who is de-risking some of the components on it and is doing environmental testing and building boards for that use case, or somebody who's building a bed of nails for that board, or somebody who's building a test rig for that board, those people we can help and save significant time. And so that's where we see kind of the best applications so far.
Tell me about the environment. It sounds like right now it's cloud-based.
Yes, that's correct.
Yeah. Do you anticipate that this will ever be available on the desktop?
That's a tough question. I mean, the desktop is unfortunately much more constrained than cloud for compute resources. As you might imagine, we drastically benefit from having access to thousands of CPUs, tens or hundreds of GPUs. So the product would have to be very sophisticated to kind of fit all the computing you need into a single desktop. I wouldn't rule it out, but what I think is more likely to happen if we got to the point where we could be efficient enough for a single computer is that we would then still be on the cloud, but then using all that extra compute to make boards that are actually better than human, right? So if we could take a high production run of 1 million boards and save $1 per board in manufacturing, that would be very, very significant and worth spending the compute on. I suspect that is more likely where things will end up. So to answer your question briefly, we don't currently expect a single desktop application.
Now, you did mention earlier about working with different fabricators, and I want to point out one of the incentives that Quilter recently added is a PCB ordering service, which its users can leverage for free prototypes of their AI designed circuit boards. So tell me more about this Fab for Free program.
Yeah. So one of the things that we're trying to do is, I mean, obviously, as an early stage company with something that is so difficult, like we are very incentivized to learn. Like what we want to do is we want to get as many people as possible creating designs, manufacturing those designs, telling us how it went, giving us feedback for what to build better. And so we're just supporting that. For professional use cases where people have their fabricators and contracts already set up, this is obviously probably not that helpful. But for people who are running a board as a hobbyist or at home, we don't want fab to be a barrier to you trying it out. And so especially if you're willing to talk with us about it or share it with other users of Quilter and let us publish a blog about it or something like that, we're happy to fund the build of the PCBA and to work with you on it.
And which fabricators are you working with those?
So far, we are tailored to produce files for JLC PCB, OshPark, and PCBWay. But in general, we do also run compilations for rules that basically any fab should be able to handle for simpler designs. And so I wouldn't rule out any of the others either.
You're looking at this as essentially like a loss leader in order to help, learn more about the whole, developing out your process.
Yeah.
Okay, Sergiy, is there anything else you want to add before we come to a close?
No, I really appreciate all the questions, and from the community, I really welcome folks trying it out and just giving us good feedback. Like if you believe this is how things should work in 5-10 years, come help us make it so.
If you are interested, you might want to go to quilter.ai for more information. I know that they have some examples, a blog, information about the company on there. Sergiy, I really enjoyed speaking with you today. Thanks for informing our listeners a bit more about Quilter and your platform. For PCB Chat, this is Mike Buteau. Have a nice day.